Hello everyone, welcome back to my channel Black Box Engineering, and in today's video I am back in LTSpice here, and I'm going to be going over a concept on logic gates and how they're often modeled. Particularly we're going to be talking about a MOSFET model of a NAND gate. The thing is, there are some logic gates installed with LTSpice, but they're like multiple port ones. So if I hit the little component thing and then I go to this digital thing, you'll see if I click and it'll have multiple inputs. This is their version of an inverter, multiple inputs for an OR. Multiple inputs for exclusive OR. So they don't have base models for the basic logic gates. So the NAND gate is the universal one that can turn into all the other gates if you set them up in the right way and right order. But anyway, so the first thing that I want to cover is the idea of comparing MOSFETs to switches, because that's how these things are being set up in the first place. We're not going to use these transistors as any kind of amplifier. These are just being used as like digital switches. So the first thing I wanted to cover is just like a basic overview of how the logic works without bringing MOSFETs into the picture, because I think it's good to like break things down into simplified concepts and then move on to a little bit more in-depth talk, because for a lot of people, and including me, when I first started learning, I thought MOSFETs were basically black magic. I didn't really understand how they worked. I didn't really we never. This was another thing that was not really explained in class. See, I think we were taught a lot by someone who didn't exactly have an electrical background. And I'm thinking that if I remember right, I'm just trying to browse my memory here. I think our teachers said that every component in like resistors, capacitors, inductors, and so on, like to model them, you have to have some kind of equation. And for the most part, it's correct. But the thing is, when something behaves in a binary way, there really isn't a good equation to model that with. In fact, it uses a whole different form of logic, of mathematical terms. Instead of using basic arithmetic, there's something called Boolean math. I don't want to really get into that too much, but it's completely different from other mathematical equations like for capacitors and inductors. And it really doesn't have anything to do with modeling how a system works. I mean, you can with digital logic. You can certainly set up equations in the Boolean arithmetic way, but I'm not going to overcomplicate this topic for now. So we're just going to keep it as simple as this thing turns off, this thing turns on. And then I also have to talk about normally closed switches and normally open switches. But suffice to say, my only point was there's a bit of an error when you're talking about equations for like MOSFETs. I mean, technically there is a little bit of current drop across a MOSFET any kind of transistor when it's on, but in in most cases we don't really care about the zero point 0.7 volt like drop really. It's, I mean, those are for BJTs really. I mean, technically MOSFETs have a voltage bias as well, but it just acts different. And for the most part, when you're talking about like digital logic, you don't really consider the zero point 0.7. When you get into like more complex designs, the voltage drop does matter. But for like the small like gate kind of stuff, like the and or nor not, we don't really consider the zero point 0.7, 0.6 volts as anything to really care about. But so let's just get into the concept first. I'm gonna just start with switches as I've said. So what I've got set up here is an equivalent of a NAND gate, but with voltage controlled switches. Since there's no way to do a physical switch in LTSpice, you can control switches to turn on and off through a voltage source, a voltage signal. I modeled up these normally closed switches on the top here. I can get into a different video if you're curious about how to do that. All that I need to make clear is the difference between a normally closed and normally open switch for those that aren't familiar. So, like imagine like you've got a clicky switch in your hands. Let's say that if you didn't press it, a normally closed switch means that if you were to provide a voltage to that switch, it would already have continuity between the switch part. So that means that from point A to point B, there's already a connection in place. And as soon as you press that button, there's a little like piece of metal that travels away from the circuit so that it interrupts the path between one side of the circuit and the other, so no current would flow through the path. So it's like a default on kind of thing, therefore normally closed. And of course, normally open means that if the button's not pressed, there's not going to be any current flow through that path because it's open. And then if you push it, it's going to close, and there's going to be metal contacts that touch two other parts. And then because you've got metal touching metal, you've got continuity or a complete path between point A and point B, causing current to flow through that switch. So that's kind of how those terms work. But anyway, at the top here I've got two normally closed switches set up kind of in parallel. I have two voltage sources controlling these normally closed switches. I'm going to call this in A voltage and in B voltage right now, because there's no voltage going to the normally closed switch. That means that it's going to stay closed. Think of that as a unpressed switch for the 0 volt thing. So 0 volts equals not pressed in this particular case. Same thing for the normally open, 0 volts means not pressed. So if we think about this, oops, I don't know what I did there. So we've got our source voltage. We see that input A is powering this switch and this switch. So since we're at 0 volts, this is going to stay closed. So we've got voltage coming through this side of the switch. And then so we've got 5 volts on this side. We're going to have 5 volts on this side. And 0 volts also goes to this switch, meaning this stays open. So there's no voltage that wants to come through this part because this switch is still open. So nothing wants to go this way towards this ground. So there's only one way it can go. It's through the switch, through this node, and then through the resistor. And then if you look at in B voltage source, this switch stays closed. So voltage also comes this way, and it's still 5 volts. And because we're not, like, it's the same voltage source, so we're not adding voltages. It's still going to be 5 volts and 5 volts. It's not going to add up to 10 because we're not adding a source. It's the same voltage source, just available at 2 points. And then because 0 volts is also going to the other switch, this switch stays open. So there's no path to ground. So we've got a 5 volt signal coming to this resistor, which means that there's going to be 1 amp. So if I hit run, let's say 2 seconds. Let me just get these. So we should see 5 volts. And if I do 5 volts at 1 amp. Sorry, 5. Sorry. 1 amp through the resistor, 5 volts available at this output node. So that's what we would expect on having 2 inputs as 0 on a NAND gate. If I were to now turn one of these voltages on, we can go through that particular step. So if I turn this to 5, so now that we have 5 volts coming to this switch, it now activates this switch, meaning that it will flip open. So think of 5 as closing the switch, but on a normally close it would open the switch. So it would open this switch, meaning that there's no continuity between this top 5 voltage and this branch here. So across this you would have you wouldn't have current coming through this switch. You would have 5 volts here and 0 volts if there was nothing else on the other side. Like imagine that this was not connected here, you would have 0 volts. This switch right here would now turn on, meaning that it closes, so you would have current going from here to here. But since the other voltage is 0, this switch stays closed, so 5 volts comes through and current is allowed to pass through this switch, through the resistor, still having 5 volts. But since this switch is closed, but this switch is open because 0 volts to the other switch, there's no path to ground here, so it can't be 0 volts, it has to be 5 volts. So that's 5. So that's 0, 0, 0, 1. If I were to switch this to 0, switch this to 5, we're gonna. Sorry, let me just hit run, just to make sure that I'm consistent here. So 5 volts and 1 amp. So, and then, come on. So the same thing happens on the opposite side. This would stay closed. This would stay closed. This circuit would open, but we still have 5 volts here. This circuit would open because it's no longer powered, but this one would close. But since there's no path to ground this way, the voltage can't come this way, so we still get 5 volts as an output. 5 volts, 1 amp. And then finally, if we turn both of these voltages on, Now we have a different situation. So since this switch is now open, the normally closed one, there's no current between this and this. And this one is positive or powered, so this switch would be open, meaning no current between this and this. So 5 volts, no current. So right now it would be like floating if there was no path to ground. But since we have 5 volts coming to this switch, which closes this switch, and 5 volts coming to this switch, which closes this switch, we have a full path from here to down to ground. We have a full path to 0 volts. So we're going to have 0 volts available on this node because it is now seeing ground because there's a complete path or current, or sorry, a complete path to the 0 volt reference point. And so we would see 0 because this is 0, this is 0, this is 0. So you would see 0 volts, 0 amps. So if I just run that, 0 volts, 0 amps. And as we see, this copies exactly a NAND gate. And this is the same exact thing with the MOSFET model, but the only difference is the technical explanation of how the MOSFET functions. So I'm going to switch over to that now so that I can kind of explain what's going on there. I might do a separate video on how on the various, like, the numbers don't matter too much on this. I did a bit of research a long time ago on this to make MOSFETs work on this program, to have a custom one anyway. The minimum that you need is length, width, something called KP, gamma, phi, lambda, and VTO. They are just parameters of a MOSFET to actually make LTSpice happy. The values, I mean, I think I just borrowed these values from other MOSFETs and I just plugged them in. For the most part, the KP, gamma, phi, and lambda don't matter too much. It's really down to the VTO. For an NMOS, it's going to be positive. A PMOS, it's going to be negative. Technically, the length and width do matter. Not on a huge scale, but they do have to be in the micro, like, realm. I don't know a ton about these, like, parameters. I just know that you have to at least have them. These values probably, I mean, they matter to a degree. They're going to change, like, how they conduct and stuff. But for our intents and purposes, we're not going to care about those values because I don't know how to explain them. I just know that you need them. That's all. So anyway, all that we need to know is different configurations of transistors. So you can kind of do the same thing with NPN transistors. There's something called a high-side configuration and then a low-side configuration. So with a MOSFET, a high-side configuration means that your gate is going to be controlling the MOSFET here, and then the middle pin, I think it's gate, drain, source. Gate is this leg here going like, sorry, let me zoom in. This is the gate. Think this is the drain, and this is the source. The source, on a high side configuration, the source needs to be connected to this first pin. These two pins act as the source, by the way. It's just important that they both go to the same point. And on high side, all that means is that the source is connected to some reference voltage, at greater than 0. So in this case, we're going to use a source voltage of 5 because that's a typical logic level that most, I mean, you can have a 3.3 volt too, or whatever logic level, but for our purposes, we're just going to use a 5 volt source. So high side, again, we're using on the source side of the MOSFET, we're connecting that to some positive voltage. And then on the drain side, we're actually using on the the positive MOSFET, the positively doped MOSFET is the technical term, but we're using this as the output. It's just like the think of it as like the, how do I put this? Current on a MOSFET always flows from drain to source or source to drain, depending on the configuration. So it always comes, current always flows from this side of the MOSFET down to this side. From, in this case, it's source to drain. So anyway, with MOSFETs, with these high side configurations on the positive MOSFETs, if the source voltage connected to the source of the MOSFET is equal to the source of the gate, the MOSFET will not conduct. It'll basically shut it off, acting as a normally open switch. And if there is no voltage on the gate, 0 volts, or if it's less than the source voltage, the MOSFET will conduct. So a positive MOSFET in the high side configuration will act as a normally closed switch if there's no voltage supplied on the gate of the MOSFET. And if there is voltage, it will open the switch. The NMOS, the negative MOSFET, or negative doped MOSFET, those ones are configured in a low side configuration. All that means is the drain is looped into ground. In this case, these two pins are looped to ground. These, technically, this is feeding into this, making like a complete circuit. We just need to make sure that at least one of the pins of the drain is going to ground. And then the source needs to be connected to the output as well, because there needs to be current flow from the output to ground if we don't want it to conduct in the case where both voltages are high, because in a low side configured MOSFET, if the gate is higher than the source, it will turn on, or in this case, like a normally open switch, if you flick it on, it'll make close contact and make a circuit complete. If the gate matches the source, or in this case 0 volts, it will open or no longer conduct. So overall, both configurations are used in combination to make the same circuit that we saw here, but with MOSFETs. And in reality, MOSFETs really are just mostly used as voltage controlled switches, but rather than having a bunch of like an actual component of a switch, these are like tiny little transistors that you plug in, and you're using them as switches, but you're just using voltage to control them instead of having an actual physical switch. Sorry, it's kind of confusing, but to just show you how, just to show that this works, I might as well add a resistor here. And move this over because on ground there would be no voltage. I think in a different video I'll show how to make this into a sub-circuit using the other method. Otherwise I'll probably go too long on this. So let's just start these both at 0. We got 0 volts coming to this MOSFET, 0 volts coming to this MOSFET. So based on what I said earlier, since 0 volts is less than the source, this will conduct, meaning that current will flow from this side, the source, through the MOSFET, meaning 5 volts here, 5 volts here. So we'll see a 5 volt output. Same thing on this one, 0 volts going to this MOSFET, and same thing to this. And by the way, since 0 is same on the gate and the source through these MOSFETs, the negative ones, they're still going to act as open switches, so there's no current flow through here. But anyway, since this is also a closed switch, still you're going to see 5 volts come through this MOSFET and through here, seeing 5 volts here as well. Again, they don't add up, but it still be 5 volts. Let me make sure that this is not that would throw things off. So if I measure this, oh right, I added resistance, so that changes things. Yeah, 5 may have been a little bit small. This is the one thing with doing logic gates. You can't ask for too much current, otherwise it will mess up like the output voltage and stuff, because it down the line it'll change things. So that's why we're seeing only 500 millivolts. But I mean, still it's technically functioning. It's just not 5 volts any longer. Again, it's different with MOSFETs than, so let's just say, I don't know, 1 kilo ohm. That's a little bit better. But there is current flowing, and now that we see that, this is a lot nicer than, and all these different like parameters is probably why it's a low current if I were to use the full 5 or 1 amp. Usually these logic gates aren't supposed to supply a ton of current. At most, like up to 10, 20 milliamps maybe, depending on the system. Anyway, if I were to get rid of this, actually, and this is usually what I don't want to connect it to ground, and just run this, we'll see a 5 volt signal. So just like an AND gate, 2 zeros will equal a 1 or 5 volts. If I were to switch these, one of the input A to 5 volts, 5 volts, it's still going to be 5 volt output, because this switch now opens because the gate is the same as the source. So through this we should see pretty much no current. I think this is in, like, if I were to measure this, femtoamps, like that's nothing. Almost. Picoamps is a lot bigger. So yeah, we see a 5 volt output still because this is open, but this is closed. This is now closed because we see 5 volts on the gate, 0 volts on the source, so it would conduct, but this is not conducting down here because 0 volts to this, so no path to ground. Switch this to 0, switch this to 5, run. We're still going to see 5 volts on the output because it's the opposite thing. So this now closes, so there's 5 volts available. This one opens, no current through here. This one opens because there's no, this is same as the source, so this opens, so no current through here to ground. And then finally, if I switch this to 5 and hit run, we're going to see a 0 volt on the output, which is what we expect from a NAND gate, because, and just to make this clear, since the source is the same as the gate here, 5 and 5, this now opens, so no current from here to here. Same thing on this switch because this is 5 here, so no current from here to here. So since we don't know what the voltage is, we need some kind of path. It would be a floating point. We don't know. So we need 0 volts somehow. And again, since the bottom MOSFETs are connected to ground, 5 volts is greater than the source of 0 volts. So this switch turns on, connecting from here to here. Same thing with this switch, which connects from here to here. And since we have a total path from this point down through here to ground, we will see 0 volts because ground is 0 volts. In reality, it's not exactly 0 volts because of all these different like voltage drops, like the 0.7 volts and all that. See how this reads as 698 picovolts? In the engineering world, that's basically 0. So you wouldn't tell the difference. In the ideal switch world, you're going to see an exact 0 and exact 5. But with MOSFETs, you're going to see not quite 5 and not quite 6. Or not quite 0. 6. Not quite 5 and not quite 0. Because of the different characteristics of the MOSFETs. So this is a model of a NAND gate. In my next video, I'll probably show how to make this into a sub-circuit using the other methods. So I hope this kind of made sense. I know that these numbers are confusing. You don't even really need like this. All this does is add a capacitance and inductance to the output. Sometimes this helps like make things run a little bit faster if it's getting complex. I guess I don't really need it, but I just like to throw it in there once things start getting a little bit more complex. Yeah, so I'm sorry that I can't really explain the characteristics of like the more like the KP, gamma, phi, lambda, VTO, length and width. That gets really deep into the weeds, and whenever you learn about MOSFETs, all that we really care about is the drain to source, the 0.7 volt or whatever the voltage drop is between the drain and source, because there's always going to be that bias, because it basically, there's a bunch of PN junctions in there, and it's not perfectly, it's always going to have some kind of voltage in there. Typically modern MOSFETs are a little bit lower than 0.7. So yeah, in SPICE, MOSFETs are a little bit more complicated. Technically, these kinds of constants do exist, but they're for like actual engineers that develop these kinds of like components. All that we care is about gate, drain, and source, and these different configurations, and then the 0.7 thing. And technically, there is resistance between whenever these are conducting. There's going to be some amount of resistance. For these logic gates, we don't really consider that, because again, most computer systems or like breadboard, like Arduinos and stuff like that, you're limited to basically 20, maybe 50, maximum of 50 milliamps per digital port. They can't really reach that level. So, and they probably don't use MOSFETs either. They probably use NPN transistors most likely. But anyway, I just kind of wanted to go over this because it's a neat topic, and I hope that you learned something. Like, comment, and subscribe. Sorry, I got kind of rambly. This is a little bit more, slightly more advanced thing, but I hope I made it easy to understand, and I'll see you in the next one. Bye.